All right, so this question here is the 2023 exam 2 question 5. So when we look at this question here, it says let f of this function equal e to the x plus e to the negative x, and you've got g right there. So it says complete a possible series of transformations to map f to g. In this case, I would look solely at this component here, where I would rearrange this so that it's g of x is equal to half f negative x plus 2. And I would write down the dilation factor of half from the x-axis. I would also mention a reflection in the y-axis and a translation of 2 units in the positive x direction. Okay, by reading this. Now, the next one here says two functions g1 and g2 are created with both the same rule as g, but with distinct domains such that g1 is strictly increasing and g2 is strictly decreasing. Okay, so with this question, I need to first have a look at what my graph looks like. And if I just pull this up, you'll see that this graph here is f1, which is the graph itself. And there's going to be, if I perhaps maybe define this, it's probably best if I define it. My calculator, so define f of x as e to the power of x plus e to the power of negative x. Okay, and I'm going to define g of x is equal to half f2 minus x. Okay, if I draw them here, this one's g of x. You'll notice that there is obviously a dilation factor in these two different graphs. However, we need to take into account that g1 is strictly increasing. So g1 is the original graph. In this case, we want to find out where it is turning. This, we get 0 for this graph. Analyze graph, 0, this graph, left. It's not letting us analyze this graph. Okay, we've hit a minimum at 2, 1. So the domain for this graph will be from 2 to infinity, and the range of this will be, so the domain, let's write this down. Domain is from 2 to infinity, and the range, and this is g1, and the range of g1 is from, what did we calculate? It was from 1 to infinity. But it's asking us for the domain and range for the inverse. So we just need to make sure we swap it around. So that means the domain of g2 g1, but inverse is 1 to infinity, and the range of g1 inverse is 2 to infinity. All right. Okay, so this next question is asking us to find the coordinates of P and Q. And P and Q are the intersection points between the graph and its inverse. In this case, we can use our CAS, and we've got the function g of x. So really, we're just trying to find out where does g of x is equal to x. And if we put this into a cas, okay, page. So we want to solve where does g of x equals x, comma, x. And in this case, okay, we get the points 1.27 and 4.08. And just keep in mind that these are the um, same values for y because it is the inverse. They will have the same coordinates. And this is 4.07, 4.07. Okay. So that's done. The next one says find the area of the region bound by the graph G and the inverse of G of 1 and the inverse of G of 2. And give your answer to correct decimal places. Now, when I see this question here, we're trying to work out the area of this whole section here. Now, I see that there is something that we could use, and the symmetrical property is something that we can capitalize on. Now, the reason why I would like to use the symmetrical property and not the inverse is because if I try to find the inverse, I'm going to need to break up the integral into two sections. Almost, actually, to this point here. I'll need to work out what that turning point is. I'll need to work out what that is, and it becomes a bit messy. So I want to use the symmetrical property, and if I know what is the integral from, so integral from 1.27 to 4.07, and the top equation is x, and I'm subtracting the bottom equation, which is g of x, d of x, I can just multiply that by 2 because I've got two of the same areas. And in this case, when you do that, you should get roughly around 5.56 units squared. All right. Now, next question. Let h be this particular function, and you've got a function where you've got a transformation, and the turning point always lies on this graph. Y is equal to 2x to the power of n. Now, in order to do this, we need to look at the original h graph. All right, so this next part here, it says the turning point always lies on the graph. Now, if we go back to our previous uh, graph, this turning point, which has a particular transformation, is always on 2, 1. Is going to be on that equation that we talked about, 2x to the power of n. This is a specific case, whereas this here is talking about the general case. So if we use this equation here, we know the specific case for this one was 2, 1. So why don't we try, if we go 1 is equal to 2 to the power, 2 times 2 to the power of n, we get half is equal to 2 to the power of n, and then we get and solve this as 2 to the power of -1 is equal to 2n, n is equal to -1. So this question is really just pretty much specifying that if you've got a general case and you've got a specific case, which we saw on the graph, but this condition matches so that it always lies on it, it means that that specific case can be applied to this general case to deduce some answers there. All right, so this next question here was very poorly answered. There are talks about using a slider to use this to find this answer. There is another way to work this one out, and we can use our understanding of um, solving on the CAS. So what we should do here is understand what the question's asking. So we've got two graphs which intersect like that, and we want to be able to adjust these k values so that when we've got a graph, we can transform the graph such that when you transform it just enough, they intersect like that when originally they were looking like this. So you want to transform the pink in a way that it eventually turns into that green and intersects only once. But we need to make sure we don't go too far with K because otherwise they won't intersect at all. So I'm going to do this using sliders firstly, and I'm going to try a different approach at the moment. So what we should do is on our graph here, I'm going to turn these off and I'm going to define, say, H1, let's say, H, Hinf, just because I want to make sure that it's the inverse that's defined as equal to got log e k over 2 plus a half square root of k squared times x squared minus 4 plus k. And it's going to ask me to potentially make a slider. In this case, it hasn't asked me to make a slider because we're not on the graphing page. But we're going to sketch h, I, and v in this case. H, I, and v. And it'll ask me to make a slider for both k and e. Okay. Those of you that know what's going on, I should have used the value e. And we'll go. And this graph here comes up. So we've got the inverse all sorted out. Now we need to define the other one. So what we're going to do is we're going to find the inverse of the inverse, which is the original. And we could do this on the cas where we actually find the inverse. However, remember the property of an inverse is that the x and the y coordinates are switched around. So I'm going to make this into a relation. And the way you do the relation is by just keep backspacing. And we're going to go x, instead of y equals, we're going to do x equals hinv of a function of y. And hopefully we'll get the inverse as you see there, which is, I'm going to change the color, line color to maybe red. So we've got the red and blue line. Now with this slider, you'll see that if I keep moving it around, it will intersect at a particular point, but we want to find the lowest point at where they intersect. And this slider is not very nice in the fact that, the intervals are very large. So what we can do is press Control menu on the slider, and you can change its attributes, not attributes, settings. So Control menu on it, settings, and the variable is still k. We want to change the minimum to looking like we want to start from 0 all the way up to, say, 5. And the step size, we want to go to maybe 0. We want to have 2 decimal places because that does say that in the question. So 0.01. Okay. So this is a bit more smooth. And in fact, we're just going to focus only on this section right here. I'm going to go to Windows Zoom in that section and in that section. And I'm going to try and see at what point they have the lowest value. So in this case, it looks like it's 1.87. That doesn't sound right. You know why it doesn't sound right? It's because my original function that I had the k on the inside, and just checking my other equation again, I forgot to put in an x variable here, which should change things. So if you were watching just a minute ago, the x was missing and the k was supposed to be on the outside. So if we've got this, you can see 1.27 seems like it is a point when they still intersect. And if we change this to 1.26, they don't intersect. And just checking 1.28, they intersect twice. So in this instance, 1.27 is our answer. K is equal to 1.27. And finally, the last question. That might be there. The last question talks about it's possible for the graphs of h and the inverse of h to intersect twice. This occurs when k equals 5. Find the area of the region when k equals 5. Now, we need to essentially find where does the intersection occur. So we want to find out essentially when does h of x is equal to h1 of x. And when we do this on the CAS, okay, so go into your CAS, and I did a quick check here to make sure all my variables were defined appropriately. And if I do a quick check here of my graphs, I've got h of x and I've got the inverse. At the moment, my k value, so I'm going to set this one to this. So my k value I need to be very careful with this one. I'm not sure if there's an interaction with these two graphs, and there is. So I'll just highlight that again. You got to be careful. If you make a slider once and you make a new graph, you can see this is the original graph that we've got. But if we go to 1.1, we've got a slider set to 1.3. The question specifically tells us the k value is 5, so I'm going to set this to 5. That graph changes, but if we go back to 1.3, you can see this graph changes as well. So be careful of the overlap of the variables in your definitions. Now, the intersection points, the area bound between the two. This is a 2-mark question, so we should probably find the intersection points. Okay, intersection, and I'll write those two exponents down. So we're trying to find the integral from 1.45 to 8.78. And we're going to go to the top equation, which is the h inverse. Subtract the bottom equation, which is the h of x equation. And if we want to work out what the answer is, hopefully this area, graph banded area, bound is 43.9139. Okay, and it's asking us for 2 decimal places, so 43.91 should be your answer for this one. Now, that was a tricky one. The question beforehand, I would suggest just getting used to setting sliders. It was very poorly answered, so hopefully this is a useful revision tool.